Hey everyone, wherever you are. Today we're going to finish up our look at the sampling distribution for X bars, average of a sample, and we're going to get going with some SAT and ACT scores. Woo! So the ACT is a score scored with whole numbers between 0 and 36. We will use this website, and there's a tiny URL there, to take samples of ACT scores from THS and ECR. Click Begin and you will see a population distribution for ACT scores for THS. So let's take a look at that. Click Begin. And here is our ACT scores for Taft. Okay, how does that look? That looks normal. Normal in the actual sense of normal. And it tells me that the standard deviation is 5. So when I come back to here, we can describe the shape, center, and variability here. So it looks like we have approximately normal. Mu is 32, and x and sigma is 5. There's no subscript here, so that implies that we're looking at the entire population. Now what we're going to do is we're going to click Animate to take a sample of 5 ACT scores. Let's animate. Where is Animate? Okay, here we go. Animate. 1, 2, 3, 4, 5. And it looks like our mean is right over here. That's right about at 16, really. Counting up everything we had on the axes, that is, we have estimated scores of 11, 12, 16, 17, and 21 for an estimated mean of 15. Now we're going to click Animate several more times, and then we'll click 10,000 to take 10,000 samples. So let's click Animate a few more times. All right, here's another 5 samples, a different set of 5 samples, and let's do a different set of 5 samples, and a different set of 5 samples. And you can kind of see that it's going to start building up a sampling distribution, or a distribution of sample means. That's a very interesting look here. Maybe a couple more, and then we'll hit 10,000. Ooh, look at that. This guy is much far away from those, and yet we got a sample that was right around the middle here. Okay, let's do 10,000 and see what... Oh! Did you expect to see a normal distribution? Huh. The mean of that distribution is 15.96, which is remarkably close to 16. And their standard deviation is 2.29. The blue bloxes make a sampling distribution for X bar. How do we know that that sampling distribution was going to be approximately normal? Well, the population was approximately normal. Therefore, the sampling distribution is also approximately normal. And I think I'm going to start typing because my handwriting is starting to disgust me. So let's move on. Now let's take a look at the distribution of ACT scores for ECR. Click Clear Lower 3 and change from normal to skewed. Okay, so let's change clear the lower 3. And then we'll change from normal to skewed. Okay, there's a skewed distribution. Look at ECR with all of these low ACT scores. What is the shape of this distribution, and why does this make sense for ECR? Okay, I'm just having a little bit of fun here with this, but it's a right skewed distribution, and it makes sense because Taft students are so much smarter than El Camino students. So now we're going to change both of the bottom 2 drop-down menus to mean, and the first one should be n equals 2, and the second one should be n equals 25, and then we're going to click 10,000 samples. Okay. Over here on our simulator, we've gone ahead and we've changed this bottom one to sample size is 2. This one over here at the very bottom is sample size is 25. We've changed them both to measure the mean, and we took 10,000 samples. And here's what we came up with. This distribution over here with a sample size of 2, this is still kind of a right-skewed distribution, although the mean is still 8.08, which was very close, exactly the same as the population mean. So we're still centered at the same place, but our shape is still kind of not ideal. Now when we get to a sample size of 25, the mean is still right on there at 8.07, which is close enough to 8.08. But our shape here is so much better. Look at that. That is a very narrow normal distribution. And look at the dramatic effect that was made on the standard deviation. We went from a population standard deviation of 6.22 to a sampling standard deviation of 1.24. So those are much better numbers to work with. And with the n equals 25, we get a approximately normal distribution with a mean of 807 and a standard deviation of 1.24. So we've decreased the standard deviation dramatically. Looking back at the population of ECR, they had a standard deviation of 622, and we got that down to 1.24 just by taking a sampling distribution of 25. So this is kind of an illustration about why large samples are so great. When we take a large sample, we get a normal distribution with a small standard deviation. That means it's going to be easier to see if we have one sample that is way out of sync with the rest of them. Let's get to our important ideas. And what we saw was something about the central limit theorem. And the idea is this. Even if the population isn't normal, like the ECR population, if the population isn't normal, if you take a sample size that's big enough, usually n is greater than 30, you're going to create a sampling distribution that is approximately normal. That is an incredibly powerful statement right there. Your life is simplified greatly if you can take a large sample, because you don't have to worry about the population shape, because your sampling distribution will automatically have a normal sample or a normal shape. You can turn any distribution into a normal distribution for the mean as long as you take a large enough sample. Now the probability stuff is basically the same stuff we did yesterday, so I think we're ready to go here. And we've got Keith, who is the manager of an auto care center. Based on service records of 3,500 customers from the past year, the time that a technician requires to complete a standard oil change follows a right-skewed distribution, mean 30, standard deviation 20. Now for a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Ken budgets an average of 35 minutes per customer for the technician to do the work. Will that be enough? Now, describe the shape of the sampling distribution. Well, we have the sampling distribution of X bar. That's important. We have a sample size of 40, so that means the central limit theorem comes into action, because for a sampling distribution of X bar, if the sample size is greater than 30, the sampling distribution is approximately normal. Next, find the mean and the standard deviation of the sampling distribution for X bar. Make sure that you check the 10% condition. Okay, so the mean is pretty easy. That's going to be the mean of the population. Now the mean of the sampling distribution for X bar is equal to the mean of the population, which is 30 minutes. So the standard deviation of the sampling distribution is sigma divided by the square root of the sample size, which is 20 over square root 40, which is about 3.16 minutes. And the sample size is 40. That's less than 3,500, which was the number of customers from the past year. So the 10% condition is true. Now remember, we need the 10% condition to be true because independence will be negligible when the 10% condition is true. And if independence is negligible, that means our standard deviation formula works. So we need independence. So 10% condition says that the sample size is small enough in relation to the population for independence not to play a factor in our calculations. Calculate the probability that the average time it takes to work exceeds 35 minutes. Just like all the other work we've done, we're going to start with a normal distribution curve. We're going to say that we have a population or a sampling distribution with a mean of 30 and a standard deviation of 3.16. Label the normal distribution across the bottom with one standard deviation and then two standard deviations. Remember, we're trying to get to 35, so we've found that 35 is between 33 and 36. Based on the location of 35, we're going to expect a number that's smaller than 16%, but bigger than 2.5%. So next, our calculations, our equations. Z is equal to x bar minus mu x bar divided by sigma x bar. That's 35 minus 30 over 3.16. That z-score is 1.582. Our probability statements ask the question, what's the probability that z-score is greater than 1.582? Taking it to my calculator, I'll go second vars, normal CDF. Our lower is 1.582. Our upper is the biggest number in the calculator. This is a z-score, so the mean is 0 and the standard deviation is 1. And that gives me 0.568. So there is a 5.68% chance that a sample of 40 cars has an average work time greater than 35 minutes. All right, and we got to finish this off now. How much average work time should Keith budget if he wants to be 99% sure he doesn't go over budget? I think we all know what's coming here. We're going to grab our normal curve, label that at normal curve 30 and 3.16, and then we decide that 1% is, well, where is 1%? 1% is on the far right of that, and so this whole thing on the far left, this is 99%. We need to get a z-score for that 99%. So we'll go to our calculator again. Here, we're going to go backwards because now we're starting off with a probability, and we got to go to inverse norm. Our area is 0.99, and keep that at 0 and 1 for now. So that gives me a z-score of 2.326. Since 2.326 is a z-score, I'm going to put it above the curve and readjust where my 1% was. And it is somewhere between 2 and 3 standard deviations. And we can go now to the same equations that we've always used. So z is still equal to x bar minus mu x bar divided by sigma x bar. This time we're going to leave x bar here because we don't know that number yet. We just know that the z-score is going to be 2.36. You can use algebra to solve this, but if you don't want to use algebra, I'll show you the trick. Before we get to the trick, you also need to write a probability statement. So the probability that z is greater than 2.326 is 0.01. And let's get to the calculator so I can show you the trick. The trick here is to go back to inverse norm, and this time change this into the mean and standard deviation, which was 30 and 3.16. This is what you would do on a multiple choice test just to get that answer out there without any of the fuss work. So we paste that, and that's going to give me a total number of minutes, 37.35. And that gives me the numerical answer. So Keith needs to budget an average time of 37.35 minutes if he wants to be 99% sure he's under budget. So that's our work for today. I think it's a pretty short one. There is not a lot, but I really think that a lot of you were thinking all of this already. I hope so. You were thinking to where this was going to eventually end up. That central limit theorem is a really powerful tool, and we're really going to lean into it once we get deeper into inference. So I'll see you later. This is the last section in Chapter 7, so good luck on your Chapter 7 test, and have a good one.